Have you ever wondered about the hidden powers of electricity? It's a force that lights up our cities and powers our homes, but its influence goes far beyond just illumination. It's not just about lights and gadgets. Electricity is the lifeblood of modern technology, driving everything from our smartphones to our electric cars. But did you know that electricity is also a powerful force in the world of chemistry? It has the ability to transform matter in ways that are both fascinating and essential to scientific progress. Get ready to explore the shocking effects of electric current. We'll delve into how electric currents can initiate and drive chemical reactions, creating new substances and materials. We'll uncover how this invisible force drives chemical reactions and creates new materials. From the process of electrolysis to the creation of synthetic compounds, electricity plays a crucial role. Fasten your seatbelts. It's time for a thrilling ride into the electrifying realm where chemistry and electricity collide. Join us as we explore the dynamic interplay between these two forces and discover the groundbreaking innovations that arise from their union. Imagine a river of tiny particles flowing through a wire like water through a channel. That's electric current. These particles, called electrons, carry a negative charge. When they move in a specific direction, they create an electric current. This flow of charge is the driving force behind many chemical reactions. It's like a magic wand that can break apart molecules and forge new bonds. One of the most dramatic effects of electric current is electrolysis. This process uses electricity to break down chemical compounds. Imagine splitting water into its basic elements, hydrogen and oxygen. That's electrolysis in action. By passing an electric current through water, we can separate these elements, unlocking the building blocks of life itself. Water, the elixir of life, is made up of two hydrogen atoms bonded to one oxygen atom, or H2O. During electrolysis, the electric current acts like a molecular scalpel, slicing the bonds between these atoms. Hydrogen gas, or H2, bubbles up at one electrode, while oxygen gas, or O2, collects at the other. This simple yet powerful process has far-reaching implications, from generating clean energy to exploring the potential of hydrogen fuel. Section 5. Shiny Secrets, the Art of Electroplating. Ever wondered how jewelry gets its gleaming coat of gold or silver? It's all thanks to electroplating, another fascinating application of electric current in chemistry. This process uses electricity to deposit a thin layer of metal onto another surface. Want to give a copper coin a silver sheen? Electroplating can do the trick. Section 6. Measuring the flow. Ohm's law unveiled. Just like we measure the flow of water in liters per second, we can measure the flow of electric current in amperes. Imagine water flowing through a pipe. The amount of water passing through the pipe per second is similar to the electric current flowing through a conductor. We can measure electric current using a simple yet fundamental formula called Ohm's law. This law is a cornerstone in the field of electronics and electrical engineering. Ohm's law states that the current, or I, flowing through a conductor is directly proportional to the voltage, or V, applied across its ends. This means that if you increase the voltage, the current will also increase, provided the resistance remains constant. Conversely, the current is inversely proportional to the resistance, or R, of the conductor. In other words, if the resistance increases, the current will decrease, assuming the voltage stays the same. In simpler terms, more voltage means more current. For instance, if you increase the voltage in a circuit, the current flowing through it will also increase, making devices like bulbs shine brighter. On the other hand, more resistance means less current. If you add more resistance to a circuit, the current will decrease, causing devices like bulbs to dim. This relationship helps us design and troubleshoot electrical circuits effectively. Section 7. Real-world wonders, from batteries to biology. The chemical effects of electric current are everywhere. Batteries, those portable powerhouses, rely on electrochemical reactions to store and release energy. Our own bodies use electric currents to transmit nerve impulses, making movement and thought possible. From powering our devices to sustaining life itself, the interplay of chemistry and electricity is essential to our world. Section 8. Conclusion. The electrifying future of chemistry. As we delve deeper into the mysteries of the universe, understanding the chemical effects of electric current becomes even more crucial. The interplay between electricity and chemistry is not just a subject of academic curiosity. It holds the key to unlocking new technologies and solutions for some of the world's most pressing challenges. From developing new energy sources to creating innovative materials, the possibilities are limitless. Imagine a world where renewable energy is not just an alternative but the norm, where electric cars dominate the roads, and where advanced materials revolutionize industries from healthcare to construction. So the next time you flip a switch or charge your phone, take a moment to appreciate the complex chemistry and electrical engineering that make these everyday actions possible. Remember the invisible forces at play, the electrons moving through circuits, the chemical reactions happening at a microscopic level, all working together seamlessly, shaping our world in ways both big and small. These forces are the backbone of modern civilization, driving innovation and progress. Keep exploring, keep questioning, and never stop being amazed by the wonders of science. The future is bright, and it's electrifying. Let's continue to push the boundaries of what we know and discover the endless possibilities that lie ahead.